Alright, let's get started. I'm gonna quickly go through some like pre-workshop stuff really quickly. So in this folder that I've made for you guys, wait, at the front. So in this folder that I've uploaded to you guys, if not, I'll just, oh, you guys can't even see. Alright, that's better. Hold on, let me quickly pull out the, wait. So this is the QR code for all my workshop notes and also my past papers. You can take a scan of that. I haven't uploaded the recap stuff yet. I will do that at the end, alright, because I haven't annotated anything yet. But yeah, quickly scan that. Alright, seems as though nearly everyone has it. Alright, cool. So in this folder that I've made, we've got some workshop notes that I've made. So I went through this in my workshop. A lot of you guys who are in my workshop already seen this stuff. Alright, I'm going to briefly go through each of them today for each topic. Then practice questions. So these are the practice questions in the middle. So you just got to download the zip file and then you'll have all your solutions for each quiz, right? Those aren't my solutions, those are someone else's. Recording is not too important. Past papers, this is what I want to quickly talk about. So there's some odd past papers from 2008 to 2012. Right? This stuff is still relevant to what we have like for your exam. The formula sheet's pretty much the same. There's just a bit more stuff at the end here. Moody diagram, same, right? Yeah, so you can still use those older ones, which actually have solutions. So 2008 to 2012 all have solutions. However, the newer ones, so 2017 onwards to 2022, don't have solutions, right? So I'm going to go through some of those questions today. And this is like last year's one. So you guys don't have access to this on Moodle, but I just stole it from there and put it in the drive, okay? Don't tell anyone, please. And yeah, so these probably aren't 100% correct, right? But it's pretty good. Pretty good. Okay, what was I going to do now? Okay, so what I'm going to cover today, alright? So firstly, I'm going to quickly go through some of the topics that you can be assessed on. So there's going to be hydrostatics. What? Okay. So hydrostatics, energy, which includes Bernoulli's equation and momentum. Pipe flow, which consists of all of these. Dimension analysis, physical models, and boundary layers. You might also get assessed on drag force, but I'm not going to go through it too much today because the questions are always repetitive. If you can do like 1 or 2 questions, you'll be able to do the one in your finals. Alright. And I've also left out fluid properties, right? Because that's literally everything. We're going to be covering it anyway throughout all these topics, right? So how this workshop's going to run is that I'm going to go through a bit of content for one of the topics, hydrostatics. Then I'm going to go through a few questions, 1 or 2 questions, right? So for example, I'll go through a bit of hydrostatics, and then I'll go through 1 and 2 questions, right? These are all past paper questions, right? So yeah, then I'll go through energy after that, then go through another question over here. Oh, not this one, this one, right? And yeah, I'm just going to repeat that throughout the whole workshop. Now, let me check if they can hear me. Yeah, okay, cool. Can they see me? Yeah, they can. Okay, let's go through hydrostatics, okay? So these are my workshop notes from hydrostatics. I'm just going to quickly go through some quick key formulas, right? So the pressure versus depth, right? We know that as pressure increases, or pressure and depth is proportional, directly proportional. So as you go deeper and deeper, our pressure is going to increase, right? And this is defined by this formula where P2 is the pressure at a deeper point, right? Unit weight, there's a few ways you can find unit weight. So if they give you SG, which is our specific gravity, let's say 0.9, alright, we know that SG is going to be our unit weight of the fluid divided by unit weight of water, alright? So we already know what unit weight of water is. It's on the formula sheet, I think. I don't know. But it's 9,810, right? In most cases, unless specified otherwise. right? And then you just rearrange for your gamma weight of the unit weight of the fluid, right? So you get times 9,810, something like that, for example. Or they just give it to you. Okay. What the heck? Okay. Measurement of pressure. So this is like manometers, piezometers, all that stuff. Alright. So I've got like a general rule over here. So you start at one point, let's say at point A, and you want to end at another point, point B. Alright. So you start at point A, you work your way through the tube and calculate the pressure differences. Alright. So for example, something like this. Right? This is straight from the lecture notes. You'd start at point A, yeah, and let's say this is given, and you're trying to find pressure at point B, right? So you start at point A, or you can start at point B, it doesn't really matter. You get the same equation anyways. Are there no seats? Okay, never mind. Where was I? So what you need to do is, if there's a fluid, oh yeah, by the way, in these manometers you'd have multiple fluids, right? All the fluids are going to be of different density and unit weight. So what these fluids actually do is that they cause a pressure change from point A over here to point A dash, for example, right? And like I'll go through how to form an equation like this with the example, but it changes from different question to question, right? Okay, in that case, I'll go through a quick question on manometers, then I'm going to go through forces on a submerged body afterwards, okay? So, this is from the 2008 finals. So, calculate the difference in pressure between point A and point B in two adjacent pipelines containing stationary water. Alright? So, they've given us that oil has a specific gravity of 0.9. So, SG oil equals to 0.9. And from this, we can actually find our unit weight of oil. Right? The way we're going to do that, as I just explained, 0.9 times 9810, which is 8829. Let's say kilonewtons per meters. I forgot the units. Meter cube. Newtons per meter cube. Is that the right units? I forgot. Give me 1 second. Yeah, it is. Okay, cool. So we see that over here we've got some water. They've explained it here. We've got some water over here and over here. And between these two waters, we've got oil. Right? So I'll just color code it really quickly. That's our oil. I should have done it in a different color. And in the purple, we've got water. So how do we write the manometer equation for something like this? Alright, I'm going to start at point A. By the way, they're asking for the difference in pressure between the 2 points. So what we're trying to find is PA minus PB. Okay. However, I'm still going to start from point A. Okay. So point A, pressure at A, and because this water ends up, let's say we start at point A, right? This water ends up at a higher depth than point A. So is our pressure difference going to be positive or negative? Negative. Perfect. Negative, and the general formula is just going to be our unit weight of the fluid, which is water, times the height difference, which is, yeah, so it's negative because it's going up, right? That's why. It's going to be 1561, so 1.651 in meters. Right? I'm going to have it in meters. Okay. So we're starting at point A, and we're going upwards, and we end at a higher point. Therefore, our pressure difference is going to be negative. Right? How about for the oil? If we start at a point here and at a lower point just to the right, is our pressure difference going to be positive or negative? Positive. Perfect. So it's going to be plus the unit weight of the oil times our height difference, which is between here and here, which they've given it to be In meters, 254. Okay? Okay, we've got one more block I guess we have to worry about. It's going to be the second water. We start at a point here and end at point B. Pressure difference positive or negative? Positive, perfect. Plus the unit weight of water times the height difference, which is this minus this. So 1.651 minus 0.50. What?
1.651 minus 2.
Oh yeah, then minus this as well. Then minus 0.254. And this is equal to our pressure at point B. Okay? So all we have to do is sub in our values and rearrange for PA minus PB. Alright? So unit weight of water, 9810. What's going on? Okay. 8829 and 9810. This question. What do you mean still? Fuck. Hey. So PA minus PB is going to be equal to 9810 times 1.651, 8829 times 0.254 minus 9810 times, what the hell is that number? 1.651 minus 0.508 minus 0.244. Syntax error. 0.889. Right, after subbing in all your values, you get 9. Five two 32.65 pascals. Alright, this is equal to 5.23 kilopascals. Alright, any questions with that question? Make sense? It's not too hard. Alright, for those, I don't think anyone's copying it down. Is there? Anyone? Still? All good? Okay. I'm going to move on to forces on submerged bodies now. Okay? So, for forces on submerged bodies, we've got 3 different cases. Alright? We've got vertical plane / vertical gate. We've got an inclined plane, and we've also got a curved surface. Yeah, out of all of these 2 are relatively pretty simple. Curved surface is completely different. Alright? So vertical plane and inclined plane, you can use like the formulas of hydrostatic force, all that stuff. However, in curved surface, you're gonna have to do some ENGG2500 mechanics. You're gonna have to do some moments about like a certain point. It's a bit like cooked, I can't lie. But here it is. So for vertical planes, I've drawn like 2 different examples. One where the gate, so all the water is going to be held by a gate. So in most of these questions, by the way, you have like a gate and water on one side or even both sides, which is a question that I'm going to go through. Right? And that water, so let's say we've got water on this left side, is going to cause pressure or like have some force acting on the gate. Alright? So it's going to be like a triangular distributed load, which we saw in ENGG2500 for the civil engineering students. I mean by environmental. But what's going to happen is that there will be like an equivalent point load due to that distributed force. Right? So we can, all that force that's being distributed along the gate, we can equate it to just being one force acting at a certain point. Right? So that force we call it the hydrostatic force, which you can use this formula. So this formula actually, no, you can't use. That's for newtons per meter. So this is like the force per meter. However, if you're given the width of the gate as well, right, you can use this formula. Right? This is, I think, on your formula sheet, or something very similar. Right? Another formula you can use is these two. So this one you can use if you have like a trapezium pressure distribution, something like this. And this one you can use like in any case, whether it's vertical or inclined. Right? The only difference between inclined and vertical is that your HC will change. Where your HC is the height to the center of the gate, right? Or the plane. So you might be wondering why this trapezium pressure distribution actually occurs, right? So we know that pressure is equal to rho GH, right? Where we take H from the top of the surface of the water, right? So if we take H being 0, being at the top of the surface, our pressure is going to be 0, right? At the maximum, it will be whatever H is, right? The height of the gate. So if our gate doesn't actually reach the surface, but it starts at a point lower than the surface, right? So we start at it over here, right? Where the surface is over here, right? There's going to be some sort of pressure already acting at the top of the gate. Right? That's why we have this pressure distance or whatever, that pressure acting at the top. And then there's also going to be a maximum pressure acting at the bottom as usual, right? Yeah, and that's when you can use your trapezium formula, or another way you can actually express it. So if you have something like this, alright, where this is P min, this is P max, so maximum pressure and minimum pressure acting on the gate. You can take the area of the pressure distribution, right? So just the area of the trapezoid, which is going to be, what's it going to be? P min plus P max divided by 2 times, but this is H. I'll call it delta H. Delta H, and because you're also worried about the actual force, the hydrostatic force is going to be the volume of the trapezoid. Right? What we found with the area is just the area per meter. So if you're also given the width of the gate, you can also times the width of the gate, and that'll give you your hydrostatic force. You can do it that way, or you can do it, where's it gone? This one. Right? 2 different ways. This is like more conceptual, like if you understand how to do it. If not, just pray and use the formula. Right? It'll work, hopefully. Okay. So, what else do we have to cover? Point of application. So, for inclined and vertical surfaces, you might also be asked to find the point of application. So I'm going to go through a question with that, right? But then there's like a general formula that's already on your formula sheet, right? HC is, I've already covered, height to the center of the gate, right? It varies for inclined and vertical. For inclined, you're going to use HC's YC sine theta. It's just a bit of trig, and I'll show you how to get to it. However, let me quickly cover this one, okay? So IXXC, for those who've done 2400, you know, or like we're in the workshop with Kaden, you guys know what IXX is, right? Your second moment of area. And it changes with different shapes of the gate, right? So if you have like a rectangular gate, right, you can use BD cubed on 12, right, which is also on your formula sheet. If you have a circular gate, it'll change. Circular gate, you've got this, oh, that's wrong. Oh, here it is. Circular gate, you're going to use PD to the power of pi d to the power of 4 over 64, which I'm also going to go through in my question. All right. Okay, if you don't want to use a formula, right, so the formula you're probably going to have to use for inclined and curved surfaces, but when it comes to vertical surfaces, you actually don't need to use a formula, right? So for example, if I were to tell you, so this is like a fixed surface, and this is our gate over here. where the gate looks like this. It's just a circle. Shit. Alright? We can actually find what the center of the gate actually is. What's it going to be? Where's the center of the gate? Center of the circle, right? This is going to be here. So if this is our, let's say, 2 meters, right? Then our center is going to be here. 1 meter, sorry. Surface, that's the surface of the water. You can find your HC. Alright, they'll probably give it to you. They'll be like, oh, if this is, let's say, 8 meters, alright, this is 1 meter down here. Then your HC, or your point of application as well, is going to be 7. So it's a bit hard. Something like that. Similar, right? I think there's some practice questions that actually goes through it this way rather than you using the formula. Right? Okay. Inclined surface. The only difference is that your HC changes, and you're gonna have to use this formula. You can't use the trapezoid formula anymore, right? Because your pressure distribution isn't trapezoidal anymore, right? Some people get confused as to what XC and YC are. You can think that if your plane was vertical, alright, this would be your YC. Oh shit, sorry. This would be your YC, which is equal to HC in this case. So YC is the center of the gate, which is equal to HC as well for a vertical surface. However, if you had an inclined surface, you'd just be inclining your YC as well. So YC will start at this point, you get something like this. So YC isn't vertical, however HC is the vertical distance to the gate. To the middle of the gate. That's why HC is. A lot of people get it confused. Alright. So HC, I'll just quickly write a note. Vertical distance to center of gate. That's our HC. Okay? Your point of application formulas change very slightly. Right? So YC actually stays the same, but your XP, instead of having IXX, right, it's going to be IXY, which means our polar moment of inertia. In most cases, it's 0. Right? So if you have a full circle, an ellipse, a rectangle, square, it's going to be 0. The only time it changes is if you have a triangle, which I hope you guys don't see for your finals. Right? So yeah, for rectangles and circles, it's going to be 0. Right? Okay. I'm going to actually quickly cover the question first, then I'll go through a bit of curved surfaces. Right? So this is a question from last year's paper, question 1, last year. Let's quickly read through it. So a circular gate separates fresh water, which is to the left over here, from salt water, which is on the right. Okay? The gate is a circular disc hinged vertically at the top. So there's some sort of point at the top, hinge, sorry, and it has a radius of 1 meter. That means our diameter is going to be 2 meters, which they've already said here. Diameter. So, what they say, the salt water level to the right is 4 meters above the bottom of the gate. So this is 4 meters. And the fresh water to the right is 3 meters above the bottom of the gate. So this is going to be 3 meters. Okay, so they've given us a density of salt water and fresh water. So a density of, let's say, fresh water is going to be 1,000 kilograms per meter cubed, and the density of salt water is going to be 1,025 kilograms per meter cubed. Okay. So let's take a look at the first question. Determine the pressure force, also known as hydrostatic force. So if you see pressure force, don't get confused. It just means hydrostatic force, right? Of the fresh water acting in the gate and its direction. Alright, so at the moment we're just caring about the fresh water and the force due to the fresh water. Alright, so let's do question A. I'm going to quickly draw a diagram. Okay, so this is our water table, and we know this is 3 meters. So our pressure distribution acting on the gate will be trapezoidal. It'll look like this. Okay, that's what it'll look like. And so the equivalent force will look something like this. Let's call it F1. Okay. So a few different formulas you can use, right? You can say that F1 is equal to gamma HCA, where A is the area of the gate. You could also use the trapezoid formula, which is this one, gamma B H2 squared minus H1 squared divided by 2. Yeah. Why is it not triangular? So because our gate, so this is our gate, right? It's already below the water table, or below the surface of the water, right? So, I'll give you an example. This is our gate, right? So the pressure distribution from the top of the water will look something like this, right? However, if our gate was a bit smaller, so let's say like this, like that, right? This pressure just above the gate isn't actually acting on the gate itself. Right? Well, I've drawn the trapezoidal, right? The pressure distribution itself is triangular, right? But I'm just caring about the ones that's acting on the gate. So this part at the top doesn't act on the gate. It's only from here downwards. Make sense? Perfect. HC? Hi. Let me take a look. What's the question? HC. Yeah, so it'll be 2 meters. Yeah. So if this is our center of the gate, HC will be height from the top to the middle of the gate. And some people have already figured out that it will be 2 meters. Reason being, our radius is 1 meter, right? So if this is 1 meter, sorry, then the rest of the distance is just going to be 3 minus 1, which is 2. Right, not too hard. So you can straight up just plug into this equation. Okay, I'm going to use the top one. So our gamma is going to be rho g, or let's say of freshwater, times gravity times hc times our area of the gate, which is pi on 4 d squared. So density of freshwater is going to be 1000 times by 9.81 times hc, which is 2, times pi on 4 times d. What's d? 2, perfect, 2 squared. So this is the diameter of the gate. Right. So plugging this in our calculator, 1000 times 9.81 times 2 times pi on 4 times 4. I think that's right. From remembering from last year. Okay, so that's, and they've also asked for which direction it's acting in. Yeah, so which way is it acting? Yeah, left or right, which one? What does that mean? Left to right, yes, okay. So I'll just say to the right, to the right. Yeah, the same thing, still correct, left to right, yeah. Hey, everyone all good with that? It's not too difficult of a question. I'm going a bit over time, but let's work on part B. Okay, so part B is asking, determine the depth at which the pressure force of the fresh water is applied onto the gate. So pretty much looking at point of application, yeah, YP. So YP is going to be equal to IXXC divided by HCA plus HC. So we already know that HC is going to be 2. Area, we already figured out, pi on 4 d squared. IXXC is going to be a bit different. So IXXC is going to be equal to pi d to the 4 divided by 64, which is pi times 2 to the 4 over 64, which you get to be pi times 16 over 64. That's not right. 0.785. Okay, therefore, yp is going to be equal to 0.785 over 2 times pi over 2 squared plus 2, which we get to be 2.125. Make sense? So if you ever in doubt, just use a formula. Okay? Always works. Always works. Any questions so far? Okay, cool. Moving on to part C. Part C is asking, determine the pressure force of the salt water on the gate. So we're looking at the right side now, over here, and its direction. So I'm going to have like a similar diagram. So the pressure distribution will look something like this. And if I were to do like the whole pressure distribution, it would look something like this. But we only care about the solid part, which is acting on the gate. So again, our HC is going to be different this time. What's our HC? 3? Perfect. 3 meters. So again, let's call this F2, our equivalent force. So F2 is going to be equal to rho G HCA. What's rho? What's our density? 1025, perfect. 1025 times 9.81 times HC. What the hell is HC? 3 times pi on 4 times 2 squared. 1025 times 9.81 times 3 times pi on 4 times 4. 947 68.5 Newtons acting towards the left. By the way, this question was 20 marks. Right? So, what's your hurdle? 40%?
Yeah.
40%. I think if you're able to do like a question like this, and then just a little bit more, add some bullshit working out here and there, you should be able to get the 40%, because there's a bit of scaling as well. Yeah. Sorry? Am I sure they scale? Yes, I'm sure. But of course it's fucked. Of course they don't scale. He's bullshitting. He's bullshitting. Hey, part D. So the depth, again, looking at the right-hand side now. So YP is going to be equal to IXXC over HCA plus HC. So in this case, we've already got everything except for HC. HC is going to be 3, I think. Yeah, it is. So subbing it into our calculator, 0.758 divided by 3 times pi on 4 times 2 squared plus 3. We get, oh shit, wait one sec.
You want to pound 4, right?
Sorry?
The area.
Pi on 4? I use pi on 4 because I've done diameter squared.
Oh, diameter.
Yeah, so you can do pi r squared as well. You
Yeah.
get just pi. Oh, you just get pi. Meters from top of, it's from surface of water. I should probably write that up here as well. Okay? Hey, part E. Part E is the part where a lot of people messed up. Right? So let's take a look at part E. Determine the total moment of the pressure forces due to both fresh and salt water about the hinge point A and the direction. Alright, so for this question you're going to have to take moments about part A. Alright. So I'm going to redraw the diagram. No, I'm not. So if this is a hinge, point A, so we know there's going to be some sort of force acting. 2.125. So it's going to be 2.125. Shit. 2.125 minus 3, 0.875. Let me figure this out. So we've got a force acting on the gate about here. So we have to find this smaller distance here. Alright? Or you could also find this distance as well. And then there's also another force acting, let's say over 3.08, it's going to be like here. We have to find this smaller distance because we're trying to take the moments. We're trying to take the moments about point A. Alright? So we already know the distance from the top of the water. Alright? But we don't know the distance between point A and the forces. Alright? Something that we're going to have to figure out. How do we figure it out? Someone help me out. I don't know how to figure it out. What's this distance? Sorry? Yeah? $1.125. Is it? Yeah, it's 1.125. Yeah, 1.125. Because we also know that this distance is 1 meter as well. Alright? This distance is going to be 2 meters. So to find this one, 3.0833 minus 2, which is 1.0833. Yeah. What's happening right now? Are you paying attention? Yeah, no, I'm sorry. No, I was just trying to figure out where the forces are going to be acting. I'll really explain it, because I didn't really explain it that well. So anyways, so we know that we've got some sort of force acting on the gate, right? Where did it go? Okay, I don't like that. Hey, there it is. Right? So there's a force 1, force 2, acting from the left and then the right. Right? So what we have to do, what the question has asked us, is that the total moment about point A. Right? So what we're trying to do is find the moment about point A due to these forces. Right? So when we're calculating moments, right, we need a force and we need a lever arm. Right? That lever arm is going to be the distance between point A and the force itself. Right? So what I've just done quickly is to calculate the distance between, just calculate the lever arms for each force. Right? So what I've done here, so if this is F1, hold on. If this is F1, this is F2. Right. Our lever arms are going to be 1.0833. 3. This one's going to be 1.125. Right? This is simple geometry to find it. I kind of struggled with that, can't lie. But what I'm going to do now is I'm going to assume there's going to be some sort of moment acting at point A. Right? Let's say MA. acting counterclockwise because we take counterclockwise as positive. Alright? So what I'm going to do, I'm going to do sum of moments about point A equals 0. Is 0? Yeah, it's 0. And pretty much, let's take a look at the forces individually. So F1, when we're acting on the lever arm, or when we're acting on the gate, it causes the gate to rotate anti-clockwise. Alright, think about it. This is our gate. Alright, I've dropped it. This is our gate. Alright, and we're putting a force here. It's going to cause the gate to move like that. If it's hinged at point at the top. Alright, if there was a gate acting like this, force acting like this, it's going to move the other way. Yeah, there. So, first force I'm going to take is going to be F1. And the reason I want to take it as positive is because it's acting counterclockwise. Right, so this is going to be F1 times our lever arm, which is 1.125. Let's take a look at F2 now. F2, the gate is moving anti-clockwise now. Right, gate's moving anti-clockwise, therefore we take minus. For those who haven't done ENGG2500, it's a bit tough. Can't lie. But, yeah. And then we're going to also add MA. What? Yeah, F1 is anti-clockwise. And I've defined anti-clockwise as positive. Yeah, F1 is going anti-clockwise. Alright, F2 is going clockwise. So we take it as negative. What? Yeah. Well, we're trying to find the moment. So, oh yeah, direction, I've assumed it to be counterclockwise. Is it? Yeah. So it doesn't matter how you put it. You can have it as clockwise as well. If your answer changes at the bottom, the only difference would just be a negative or a positive. Right? So let's quickly find MA. Sorry, F2. F2 is up here. Alright, and then there's going to be, plug in your calculator. Let me see what you get. Seven, 5, even. And it's going to be going anti-clockwise because our answer is positive. Make sense? Because our answer is positive at the end, it's going to be anti-clockwise. Any questions? Claudia? Confused? I know you're not. Okay, if you have any questions, I can explain it. All good? Okay, perfect. Oh yeah, that's our final answer, I think. Alright, if there's no question, I'm going to move on to... Oh yeah, sorry, this is another question, by the way. This is from... I forgot what paper, but it's a pretty good paper to do. Question to do, right? So this is when you have a circular gate. This is a curved surface question, by the way. So you have like this being your curved surface. Wait, shh. This is your curved surface, alright? And you've got water on the left and the right, alright? So you have some sort of hydrostatic force like this, and another hydrostatic force like this, blah blah blah. However, you also have these weight forces. So there's like little pockets of water that also act on the gate. Or not really on the gate, but they're like horizontal, vertical forces, right? So when you're doing curved surfaces, you have to find both the forces acting in the x and y direction. So horizontal and vertical forces. And at the end, what you're going to have to do is do like some force resolution. So after you find fx and Fy. So by doing sum of forces in the y and sum of forces in the x, you can find your F, which is equal to, you can do that. Find your total force, and to find the angle that it's acting at, it's going to be tan inverse. Okay. Yeah, that's pretty much it for curve steps. Now I'm going to go through the question. The solutions I've already put down here, I'm going to upload them as well. Okay? So I'll just quickly go through the solution. So we've got some pressure force acting on both left and right. Wait, shh. Wait. Pressure force acting on both left and right. But then the vertical forces acting per unit width. This is going to be gamma times V. That comes from our buoyancy formula, right? So that's just the weight of the fluid, right? So I'll just say weight. Right? Is there an aircon button? Okay. Yeah, and then you see that after you find your vertical force and horizontal force, you can plug it into the formula, find the angle it's acting at, blah blah blah. Right? Okay. I don't think we have time for this question. No, but it's just a Bernoulli's question, right? We're gonna go through a lot more Bernoulli's later on. Like, this is just like the most simple case where you neglect any losses. So no friction, no local losses, nothing. Alright, we'll go a bit harder, do a bit of local losses, frictional losses, blah blah. Alright. And this is from the 2024 paper as well, by the way. So you can find solutions to it over here. I don't know, I'm pretty sure you're like close to full marks. Yeah. So you did really good. Go on better, bro. Alright, momentum. Let's take a look at momentum. Nope. I'll also go through a bit of energy, why not? So this is our Bernoulli's equation, right? Total head. Just plug in all your values to the Bernoulli's equation, right? We've got something called pressure head, velocity head, and elevation head, right? These really matter when you're trying to find your total head line and your hydraulic gradient line, right? When you have to draw them, right? So I'll go through them in a bit when we get to the pipe flow pressure. Right. But yeah. So if our energy is conserved, or assuming there's no energy loss, right, the total head at any point throughout the pipe is going to be the same. Yeah, no matter what. So if you have like, so let's say no energy loss, right? So you take any point, all the heads are going to be the same. So H1, blah, blah, blah. Total head is going to stay the same. However, if we have something called head loss, or when friction is present, right? There's actually a different definition of head loss, right? But let's call it frictional loss in this case, right? We have to sub in. Shut up. We're gonna also add a head loss expression, right? The general equation for a head loss is going to be K times U squared on 2G. K is a coefficient they usually give to you, right? In the case of friction, you're actually going to have to find it yourself, right? That's all in pipe flow, if there's frictional loss, where you're going to have to find Reynolds number first, then use the Moody diagram to find F, sub it into this equation over here, and then this is your head loss due to friction. Right. There's also something called discharging jets. I've actually got a question which covers something like this, so I'm not going to go through it now. And these are just like steps to solve your general Bernoulli's equation question. Right? So you can use continuity, or you can use your hydrostatics monominate equation to find your pressures, because usually then I'm going to give it to you. And then after you do that, you can finally write the meaning. So like this is step one, this is also step one, right? It's depending what you need. So if you need velocity, use your continuity equation. If you need pressure, use your manometer equation. Right? And then you just sub it in. Momentum. So when you're taking a look at momentum, right? This the left-hand side considers all your external forces, right? So this could be due to pressure, any extra forces acting on, or any extra forces acting on the system, right? So if you have like a tube, there's like some sort of external force like this, you're gonna have to account for it in momentum, because it's gonna affect your momentum, right? And what we have on the right-hand side is what we call our momentum fluxes, right? So there's two different ways we can express our momentum flux. It's gonna be in our x and y direction, right? So in our x direction, you consider only the velocities and flows that's going to be inputting and outputting in the x direction. For y direction, so sum of forces in the y, we're going to be looking at only the y direction velocities and flows, right? So this was a question in the quiz 1. Horrible. I'm sorry. Good math. Something like this, right? These are a pretty trash diagram, but okay, so you have some sort of inflow, some sort of outflow, some sort of outflow. Right, so in this system that we're looking at, right, in the x direction we have both an inflow and an outflow. How about in the y direction? Do we have an inflow? No, how come? Because there's literally like nothing getting input in the y direction, right? How about outflow? Do we have anything outflow in the y direction? Yeah, we do, right? This one up here. Alright? So when we actually plug into our formula, so let's say this one over here, our inflow, we can just cancel that out. It's going to be 0. Because there's no inflow in the y direction. Right? However, for the top equation, we're going to have to sub in for both outflow and inflow. Okay? So get rid of this. Yeah, so when it comes to forces, right, and we're talking about pressure forces specifically, we use hydrostatics when it's like a free surface flow, right? I've already discussed that a lot previously, and also Bernoulli's when we're having a pipe flow, right? So in this question that we have, let's say for example like this, we have a pipe flow, right? So we're gonna have to use the Bernoulli's equation to find our momentum and all that, right? This is also considered a pipe flow because you have a pipe, something like this, and water's flowing through like a closed conduit sort of thing, right? At both ends it's like kind of open, but we don't really care about that because we care about the control volume, right? The control volume for this question is going to be within the pipe, so we're going to have to use Bernoulli's at one point. Which should I cover control volumes? No, actually. It's part A. What is control volumes? I don't know. I wrote it wrong. Let's take a look at part B. Actually, no, for your sake, I'll look at this guy's answer for part A. Okay. So, steady state, right? So your system is going to be in a steady state. Your flow stays constant, essentially, right? And the control volumes include, this is actually really important. Yeah, so control volume includes all the forces acting on it, right? So we know there's a force, external force acting here, right? Fx. They've given us a value of 4,000 newtons, so we have to include that in our control volume. So our control volume will look something like this. Alright. And over here we're going to have to add this force, Fx. Right. So the control volume is pretty much the volume we're looking at when analyzing the system. It's pretty much all it is. Right. Okay, so determine the velocity at V2. Oh wait, I should probably go through the question. So, water flows horizontally in an open channel and is diverted by an inclined plane. So the channel has a constant regular cross-section. So this cross-section over here is actually rectangular. You can't assume that it's circular, they tell us it's rectangular. Right? The depth at section 1 and 2 is 1.12 and 0.3 meters respectively. And it's also inclined 20 degrees to the vertical, sorry. Okay, let's see. They've also told us this is 4,000 newtons. Okay. So let's figure out how to do this question. We don't know what V1 is, but we don't know what V2 is either. Right? So, what do we do? Let's take a look. Let's firstly, okay, by the way, one more thing I want to cover. So our momentum uses this formula, right? Is it true that our Q in is equal to our sum of Q out? In this case, yes, right? It is true, right? Because we're in a steady state, so the flows in and out have to be equal, right? So what I'm going to do firstly, I'm going to use this equation, right? The main reason I'm going to use this equation is to express my V2 or V1, or V2 in terms of V1, because we don't know what V1, V2 is, right? But at one point we're going to have to figure it out. So therefore we can say that V1A1 is equal to V2A2. V1 we don't know, we're going to call it V1. A1, because it's a rectangular section, is just going to be our width times height, right? VH. Wait, they haven't told us what the width is. We're going to assume it's 1. Right? And I'll tell you why. So it's going to be 1.22 times 1 is equal to V2 times 0.3 times 1. So if I draw this in like a 3D way, where'd it go? Pretty hard to draw, I can't lie. Something like this, right? Imagine this is our plate. They haven't given us the width here, so we can't actually find like the forces acting on it. What we can find is the forces per meter width. Alright, so if you assume it's 1, assuming the width is 1, we can find the force per minute, force per unit width. Right? So I'm going to say V1 is therefore equal to 0.3 over 1.22 times V2. 0.3 divided by 1.22, 0.246 V2. Okay, so we've got that. We've got a velocity of 1 in terms of V2. Right? And this will be very helpful later on, and I'll show you why. Because when we want to plug it into our equation up here, our momentum equation, right? If we don't have V1 in terms of V2, we're going to have two variables that are unknown. We're going to have V1 and V2 that are unknown. Right? However, if we can make that the amount of unknown variables into 1, we can actually solve V2. Right? Which is what they've asked us, right? Determine the velocity of V2. So, let's go back to this equation. What the? So sum of forces in the x direction. What external forces do we have? 4,000? Positive or negative? Negative, perfect. Because it's acting in the left, towards the left. So let's take a look at our outflow now. So we've got density times Q out times V out, which is actually just V2, right? Because V2 is the velocity going outwards, V1 is the velocity going inwards, right? Next, we have density times Q in times V1. Okay. For Q out, right, we know that Q out is going to be equal to velocity of 2 times area. Q in is going to be velocity of 1 times area of 1. Right, which we kind of already found up here, this stuff. So we're just going to solve it back in. Alright. I'm going to run out of space. 1,000 times V2 times A2 times V2 minus density, which is 1,000. Oh, the reason it's 1,000 by the way is because it's water. Alright, they haven't given us the density of water. We're going to assume it's 1000. Alright, V1 times A1 times V1. Okay, so 1000 times V2 squared times A2, which is just 0.3 times 1. So 0.3 times 1 over here. And then minus 1000 times V1 squared times 1.22 times 1. Okay? So now I'm just going to sub all this in again. 300 V2 squared minus 1220 times V1, which we know what it is, 0.246 V2 squared. Alright? Now instead of having two unknowns, V1, V2, we now have 1, which we can actually solve for, because we know this is minus 4000. So right hand side we get 300 minus 1220 0.246 with a sec. Yeah, I'm getting an odd number. I'm not getting the right answer for some reason. 0.246. Oh, 0.246 all squared times 0.246 all squared. So 300 minus. Wait, give me a second. Okay, so he somehow got him this. Oh, 0.3. Wait a second. I'm doing something wrong. Alright, I see what I've done wrong. Alright, so in this case, when we're looking at discontinuity, right, we don't have to care about the angle. Right? All we're caring about is the velocity going in and the flow going out. Right? However, when we're taking a look at forces, this is something I completely missed. We're going to have to take a look at the angle that the forces are acting. Right? Or the velocity at least. Right? So our velocity if this is V2, we have an angle of 20 degrees. Right? So we actually care about in which direction the velocity is acting. You can't just let it be at an angle, right? Because we're looking at everything in the x direction. Right? So this is going to be V2 sine 20 degrees. Right? So we're going back to our equation here. If this is V out, this should be V2 sine 20 degrees. And same thing over here. This should be V2. No, this should just be V2. Alright? So over here, I should actually have a V2 sine 20 degrees. And I should also multiply down here by sine 20 as well. So this does not become 300. Instead it becomes 0.3 times 1000 times sine 20. Sine 20 all squared, sorry. All squared. Sine 20, sine 20, sine 20. What the hell? Yeah, it should be sine squared, but where am I getting that sine squared from? Yeah, V2 times V2, right? This should actually be V2 sine 20 as well, sorry. Sorry. So yeah, so we've got V2 squared, then sine 20 all squared, so this becomes 35.09. I wish I did this question last night, I don't know Right, so 35.09 minus 1220 times 0.246 all squared, minus 38.736 V2 squared. Now we can just solve for V2. you get 10.17. So the Q out that we're looking at, right? That's also going to be in the x direction, right? So that's why I've taken V2 sine 20. So it's going to be outwards, always in the x direction. Sure. So it's a bit loud. So we're going to take a look at pretty much Q out in the x direction and V out in the x direction as well, which both are affected by our sine 20 degrees. That's why I've added sine 20 here, here, and then it's going to be sine squared at one point because you get sine 20 times sine 20. I think I might have been confused some people, but anyone have any questions about that? I can explain some parts. How to get V1? V1 up here. So just with normal continuity. Alright, because one of the assumptions is going to be that we're in a steady state, which means our flow in and flow out is going to be the same. Alright? Sorry? No, it's sine squared. Should be sine squared. Yeah? Yeah, 20, sorry. Yeah, 20. Yeah. No, we did solve for V2. Yeah, that's not answer. No. Yeah, that's what we got last year as a question. So you can expect something of this difficulty. Which in reality isn't terrible if you can see this over here. And the thing that I messed up on, the angle. Yeah? Is doable? Is it? Can you cheat in the exam? Up to you. You can try. No, it will be like a room like this. No, it will be individual desks. Okay. Yeah, question? Sorry? Yeah. They'll give you like 1 mark. Yeah, for trying. Right? But if you get it wrong, you're not gonna get the full marks. Right? Yeah. So let's say even if you got your final answer wrong, right, and you had all the working out, you'll still get most of the marks. Right? So they don't really care about what your final answer is. They just want to see that you understand what the hell's going on. Right? So you understand steady state. You understand how to use this thing, which I luckily forgot, and then you get your final answer. If it's wrong, it's wrong. They don't care. If they see that your steps are all correct, they'll give it to you. If you make like a simple mistake in like calculation or your calculator, it's not that deep, I think. Okay, let's move on to. Alright, here, I'll give you guys a break first because it's been an hour. So I'll give you guys a break for like 5-10 minutes. Then we'll go through pipe flow, dimension analysis, and physical models. And if you do have any questions about what I've just gone through, just come to the front. I can always explain it again if you're too shy. I'll pause the recording. Okay. Fucking hell. Shut your bitch ass. Shut up. Okay. So, I'm gonna go through a bit of pipe flow now. Just really quickly. So head loss, friction, all that stuff. Reynolds number. Alright, so Reynolds number, we use it to find out whether our flow is going to be laminar or turbulent. Alright, this is the third one called transitional flow. We're going to stack it, right? Because we actually, like, even right now, I'm pretty sure like people don't know what the hell transitional flows are, like actual scientists and all that. So we're going to take a look at laminar flow, turbulent flow in this course only. This is our Darcy-Weisbach equation, which we use to find the frictional head loss due to friction. Alright? That is on the formula sheet, yeah. So what I'd recommend you guys do is like you guys look through the formula sheet, like kind of annotate the formula sheet. You're not going to be taking it to the exam, right? But it kind of helps with what you know and what you don't know to prepare for your exam, right? So in this equation, we're going to have to find something called the friction coefficient, right? Friction coefficient we find by using our Reynolds number, right? So if we have laminar flow, right, you can just straight up use this equation to find our friction coefficient, right? For turbulent flow, right, which is just after, there's 3 different flow regimes, right? I think that's what it's called. There's turbulent flow, smooth turbulent flow, fully turbulent flow, and then there's transitional turbulent flow. Alright, so for each of them, you can actually use, what's it called? Moody diagram. Alright. However, there are some equations that you can use as well. I don't think all of these are on the formula sheet because they expect you to use Moody diagram. But if you go in and memorize it, I think they won't mind if you use them either. Alright. But for laminar flow, you're expected to use something like this. Alright. So turbulent flow, if you have smooth turbulent, which these are covered in boundary layers by the way, it's like your ratio of boundary layer thickness to roughness. Alright. When it comes to smooth turbulent, we can just assume there's no pipe roughness at all, right? So in the question that we won't actually give you pipe roughness at all. In most cases, if they give you pipe roughness, it will be fully turbulent, fully rough, okay? So this is a pretty simple equation. Fully rough turbulent, it's a bit of a harder equation, so I recommend you guys use Moody diagram for fully rough, okay? The other one is transitional. There's literally no way to solve this. So you're going to have to use Moody diagram as well for that. Right? So if you're ever in doubt, just use Moody diagram. Always works. And the way you can use Moody diagram, I'll probably go through that as well. So you obviously find your Reynolds number, right, which is going to be here, at the bottom, sorry. So you just draw a vertical line up from your Reynolds number. Then you're going to find your relative roughness, right? If it's, where is it? Where's the number? Here it is. So these are like your relative roughness, right? So if you get 0.1, you're going to actually form a curve, right? So all your relative roughness things are all going to be curves, right? So these curves that you guys see here are all your relative roughness, right? And wherever the point of intersection is, right, that's your friction coefficient, okay? Yeah, it's pretty much how you use Moody diagram. Local losses, so these are when you have contraction, expansion, entry, exit losses, or when you have like a valve as well, right? So the general equation for like a local loss is that you have a, what the hell does that say? Oh yeah, minor loss. You times it by your coefficient, so that's going to be your loss coefficient, and you multiply by your velocity head, v squared over 2g. And you do that for each one of your losses, local losses. So if you have, let's say, a bend, exit, entry, valve, let's say you have 4 of them, you're going to have to do it for each one of them, okay? So entry losses, obviously, when you have entry, exit losses, when you have an exit. Yeah, it's pretty self-explanatory, right? So in most cases, they're going to give you the value of k. Not in most cases, in literally all cases, in your finals, you're going to have to find k yourself. Oh, I'm sorry, they're going to give you k, you're not going to have to find it yourself, right? Because it changes from question to question. You're going to have to, fucking hell. You're not going to memorize this table over here, or like this table over here. They're just going to give it to you, luckily. Yeah? So in this question, over here, this is a question 3 from 2019. Alright, so it shows a pipe system carrying water. They've given us the flow, blah blah blah, bunch of all of this. Okay, so we have a local loss coefficient of 0.4 for a bend. So we've got a bend here and a bend here. Alright, so there's going to be 2 local losses that we have to take into account. We've also got a valve which has a loss coefficient, so that's another one we're going to have to take into account. Then there's also an exit loss that we have to take into account as well. The entry loss, it's not really an entry. The diagram's a bit misleading. It's not open to the atmosphere. In fact, it's like this. It continues on. It's a bit, yeah, question? This one over here? Yeah, we'll take it as a bend as well. Yeah, it's actually meant to be. So 1, 2, and 3. Usually nozzles are like this, so there's no bend, but if there is a bend, you've got to take into account as well. Okay. Oh, actually, let's read the question. Yeah, it's a bend. They've also given us L, which is the length of the pipe, which is useful for our friction coefficient, right? So let's take a look at part A. In the first approximation, calculate the pressure at location 1, neglecting all losses in the system. So in this case, we're not going to take a look at entry losses, exit losses, any of that BS, right? Or friction losses, right? So we're just going to do A. Oh shit, okay. So, where is it? Calculate the pressure. This is just going to be using Bernoulli's equation. Alright? So we know the pressure at point 2. What is it? Pressure at point 2. 0? Yeah, perfect. It's open to the atmosphere. Yeah. So we're going to take Bernoulli's equation at point 1 and point 2. Right? So horrible. V squared on 2G. 1 is equal to Z plus the reason I can say this is because they've told us neglecting all losses in the system. Right. Okay. So we're gonna have to find V1 and V2. Right. They've given us delta H to be, where is it? 5 meters. Where'd it go? 5 meters. Here it is. Alright. Okay, so also because we're neglecting because we're neglecting all losses, that means the flow stays constant. So the flow over here is going to be 1 meter per second, and over here it's going to be 1 meter per second. Alright. So will our velocity be higher at point 1 or point 2? The flow stays the same. Exactly, perfect. So because it's the less diameter at point 2, right, our velocity is going to be higher. You can think about it, if you're trying to push something small through a smaller diameter with the same pressure, it's going to go through faster, right? Yeah, you can also think about the equation. So Q is equal to VD squared. If our D decreases, our V has to increase to compensate for the loss of D. So the velocity is going to be higher. Right? So let's take a look at point 1. So Q is equal to 1 meter per second, which is 1 times 10 to the minus 3 meter cubed per second. That's a S, cubed per second, which is equal to V times A. What we're trying to find is V, right? Because looking at the Bernoulli's equation, we don't know what V actually is for point 1 or point 2, right? We know what we're trying to find is pressure. We know this is 0, 0, and we can actually find the difference in elevation. In fact, they actually give it to us to be delta H. So if you take this as datum, right? The difference between point 2 and point 1 is just 5 meters. Right? So I'll note that down. Z2 minus Z1, which is delta H, is 5 meters. Right? Okay, let's try to find velocity now. So velocity times pi over 4 d squared. Velocity times pi on 4. Our diameter of the pipe at point 1. Let's say 5 centimeters. Yep, exactly. Times 0.05 squared. So just rearranging for V now. We get 1 times 10 to the minus 3 all over 0.05 squared times pi on 4. 0.509. Right, so that's our V1. At point 2, I'm going to do something similar. Q equals to 1 meter per second, which is 1 times 10 to the minus 3. Am I recording? Yeah, beautiful. Meter cubed per second, which is equal to V2 A2. This is V1 A1, V1, V1. So I'm going to do the exact same steps. V2. One sec. This is going to be pi on 4 d squared. The diameter at the nozzle, or the exit diameter, is 1 centimeter. 1 centimeter, sorry. So I'm just going to sub in for 0.01. So you get 12.73. So it's like a huge difference in velocity between point 1 and point 2. Question? No? Okay, so there's like a huge. Can you guys hear me, by the way? Okay, cool. Okay, where was I? Oh yeah, time to find the pressure. So what we're trying to find is this pressure here. Oh, this one. Alright. We can find Z2 minus Z1, easy. We can find velocity head at point 1 and point 2. So let's sub it in. Sorry? Wait, what does it say 2? Provided. I can't find it. Where the hell are you guys seeing this? Last row?
Yeah, no, go on. Yeah.
Oh. Alright, so. Sorry, I'll just use 2 centimeters. Yeah, let's use 2. So you get 3.183. Okay, so yeah, we're using DS2. Yeah, I did not notice that. Wait a second. Okay, never mind. So this is going to be that plus V2 squared on 2G. We know that P2 is 0. We know that Z2 minus Z1 is just 50 centimeters, was it? 5 meters, sorry, 5 meters. V1 is 0.509. This is 3.183 squared. Alright, so rearranging for our pressure head 1, you get 5 plus 3.183 squared over 2g minus 0.509 squared over 2g, which you get to be 5 plus 3.183 squared over 2 times 9.1. Oh shit. 5.503. Therefore, P1 is going to be equal to that times 53.99 kPa. Okay? This is about a bunch of calculation once you actually understand how to do this part. Okay? So one thing to notice, the reason I've used Q equals VA is because we're in like a, what is it? We're in a pipe. Yeah, we're not using any manometers, we're not doing anything like that. We're just in a pipe. So I'm going to use the continuity equations. Or flux equations. Any questions? Alright, let's take a look at part B. KPA. So, yeah, all good. So, in a more detailed assessment, calculate the pressure location, including all losses. Alright? So if we take a look at point 1 and point 2, we're going to have some sort of head loss, delta H. This delta H, right? We've got to account for the 3 bends. We've got to account for the valve. We've got to account for the exit. What else do we have to account for? So we've got the bends, exit, and also friction. Okay. So what we have here are all just like the head losses, which includes local losses and frictional losses. Alright? Okay. 1, 2, 3. Okay, sick. So what I'm going to find first is going to be the frictional loss. So this is HL. So HL is going to be equal to friction over dot V squared on 2G. Okay, to find our frictional loss, first of all, we're going to have to find our Reynolds number, which is Vd times density over our viscosity. Okay, let me quickly find out what the velocity and stuff are. Oh, the viscosity. Oh, lovely, they haven't told us. Right, for this case, you're going to have to use your, they've told us that it's just water, right? Yeah, water. So we're going to have to use our formula sheet. So let me open up the formula sheet. So all your values are up here, right? So what I'm going to use the dynamic, kinematic viscosity. So velocity, I'm just going to use V1, or like a mean velocity, which is 0.509 times our diameter of the pipe, 5 centimeters, over 10 to the minus 6. Which is greater than 2000, therefore turbulent. Okay, so what's the next step? Finding out friction factor. So in this case, how can you find friction factor? Are you sure? They've given us roughness. Right? So let's actually use the roughness formula. So let's take a look at relative roughness. So the reason we find relative roughness is because it's what's on the Moody diagram. Right? Relative roughness. We're trying to find K or something. Right? Which is equal to, they've given to us in millimeters. What is that in centimeters? 0.25 divided by 10, 0.025. Centimeters. And then you have your diameter of the pipe, which is 5 centimeters. Which you get to be answer to 0.005. Okay? So now to find friction, friction coefficient, we use Moody. That's its coefficient. Okay, so we've got our Reynolds number to be, what is that? 25450. 25, or let's say approximately 2.545 times 10 to the 4. So going back to our Moody diagram, this is going to be approximately here. Oh wait, over here. So I'm just going to draw a straight line from there. This is 10 to the power of 4. So 10 to the power of 4, then you're going 2.5 over, lines over. Okay? Sorry, question? That makes sense? Okay. Alright, I'm just going as high as I want. Next thing is our relative roughness, 0.005. Let's try to find it. Where is it? 0.00. What the hell? That's so stupid. Okay. Anyways, let's draw a line. It's much easier on your paper than iPad. I've already got it wrong. This is going to connect with this line here. How do I do what? Because it converges. So this line above and this line at the bottom converges at one point. Look. So I put it like it kind of converges at one point, right? The middle point. So I just let it equal to that. Yeah, the accuracy does matter, sort of, but not that much. Right? As long as you've shown that you really get it wrong. Because for these kind of questions, there's going to be like some sort of margin of error. Right? So there'll be like a minimum and maximum answer. And then looking to our left, we get, what number is that? What the hell? 1, 2, 3, 4. Yeah, 0.33. Alright. Why is it 325? Alright. If you have 0.3, 0.33, 0.35, doesn't matter. Alright. This is the approximate answer. Alright. So we can find HL now. Is it 60? Yeah, that was 60. Which you get to be .515. Yes. So that's our frictional head loss. Okay? Question? Any questions? Explain again. Sorry? Yeah, question, go ahead. This one? Okay, so the velocity, first of all, because the pipe itself is like constant until the very end, right? I'm just going to use the velocity of the flow at the beginning, right? I think you're meant to use like a mean velocity, but you can use both, doesn't really matter. Right? Because they haven't really given us mean velocity. And we don't know the velocity throughout the entire pipe, like here as well. You can just use V1, right? It doesn't really matter. D is the diameter of the pipe, right, which is 5 centimeters. And the kinematic viscosity, I've got from the formula sheet. Down. Right? It's kind of annoying they have it as V instead of the actual letter. But now you guys know that that's going to be our kinematic viscosity. Wait, shh. Does that make sense? David? Make sense? Alright, any other questions? Alright, so we found frictional loss. We have to find the other losses as well now. We have to find the bend, the valve, and the exit. Okay, so let's try to find the valve. Zero point 0.5. Right? Yeah. I don't know. This is a loss. That's what you gotta know. At the valve. Right? They've kind of told us as well that there's a. No, I don't know, man. So plug it in, 0.5. Alright, so that's for the valve. For the exit, K exit is equal to 1. It's 1. And we also have the bends, right? But for the bends, how many bends do we have? 3, right? So we're going to have to multiply by 3. So for bends, what's K bend? For the bends, they've told us that it's 0.4. Zero point 0.0158. Alright. Nicholas, make sense? No? What are you confused about? Which one? This one? Alright, so what I found, so using the K valve, what I found was a head loss at the valve. Alright, what I'm going to use that is I'm going to sub it in to find out overall head loss. Alright, once you find out overall head loss, I'm going to plug it back into our Bernoulli's equation, and you can find pressure that way. So the difference between this question, part A, and part B, is that in part A, we didn't care about any losses. Alright, so we didn't have to do all, like, find the delta H overall. Alright? So that's something different. So this one is a bit long because there's so many losses, right? There's friction, exit, valve, and 3 bends, right? But that's pretty much all the calculations for delta H, because we can actually find it now. It's going to be 0.0158 plus 0.0132 plus 0.0635. What the fuck? And we're going to add our frictional one as well, 515. Plugging this all in, 0.0158 plus 0.0123. You get 0.6075. So going back to our Bernoulli's equation now, H1 is equal to H2 plus 0.6075. This head loss, right, it's always going to be on the right hand side, or the H2 side, right? Okay, let's continue on. Yeah, question? The exit. Oh, these are wrong velocity A. Yeah. Zero 0.006. How come? Wait, firstly, I've got to fix up the exit one. So the exit, use V exit. V2 3.183. Oh wait, actually, we don't know what that velocity is. because the velocity decreases overall. It gets lower and lower and lower, so we don't know what the velocity actually is. Yeah. Well, I'll answer your question in a second. Sorry? Zero, zero? Oh yeah, you should, sorry. Where was it? 006, this one? Yeah. And you know what? I'll quickly check one thing. One sec. Let me do some secret business right now. Give me 1 sec, bear with me. 1 sec. Okay, so what I've got open here is actually all the solutions to all the path vectors on Moodle. Alright, I've decided to reveal this now. And what I'm going to do is I'm actually going to check the solution. Sorry? No? This one, right? You guys will have access to it. So we've done that. Hey, that's fine. Oop, we got it wrong. What's the velocity? Oh yeah, they've done 0.02. Shh. Hey. So we've used 0.0325, but they've used just 0.03, so it doesn't really matter. Alright? I'm gonna check this out really quickly. Bend times 3, yeah, we got that. What the hell is that? Oh wait, what? Nozzle. Oh, so they've got the nozzle. They've got the bend times 3. They've got the, what the hell is this? Oh, that's for the valve. And then you're gonna have to add that at the end. Hey, what velocity have they used? V2, yeah. Sorry, you meant to use your nozzle velocity. Yeah. Alright. So going back. So the velocity over here is meant to be 3.183 because we're taking a look at the exit velocity at this point. We're meant to look at the exit velocity at point 2. Huh? Yeah. Yeah, we use V1 for the rest. Give me 1 sec, so we get 0.516. That's fine, that's fine. V2 we figured out at so, yeah, I get what you mean, Yeah, so, you assume there's no head loss, right? But, you can't really find the velocity otherwise. Yeah. Yeah, it's a bit of bullshit. Okay, where was I? .516 plus .515. Alright, shh. So for your overall head loss, you get 1.053 meters, 1.053. Okay, now the hard part is to find our pressure. Shh. Hey, question? David? No? Okay. Pressure plus V squared on 2G. Z plus pressure at point 2 plus 1.053. I should probably cross-check my answers though. Holy shit. They've got a completely different answer. But to be fair, the head loss was different as well, so. Yeah, we got that. Alright, so they use a different value for Moody diagram. So that was different. So we're just gonna do it this way, even if I get it wrong. So we know what Z2 minus Z1 is. This is gonna be 5 meters. You know this is 0. We know what V2 is. We know what V1 is, right? Assuming that they stay constant. Right? We're gonna work with that assumption. Otherwise, you can't actually solve the question. Right? So what we're trying to find is going to be P1. So just rearranging, we're going to get P1 over this equals to 5 plus V2 squared minus V1 squared over 2G plus 1.053. Which you get to be 5 plus 6.556. P1 is equal to 9810 times 6.556 times, that's the shape. 32 kPa. Alright, in regards to the, question? So, in regards to the V2, I will check that really quickly afterwards. Sorry? Yeah. It's really close, yeah. But I have to check about V2. What the hell is that? Okay, wait, look, is anyone still coming down? Because in your booklet, I'll skip that. Alright, I recommend you guys try part C and part D yourselves. Because I just want to go through this last dimensional analysis question, right? I feel like it's really important to understand dimensional analysis. So for dimensional analysis, these are steps you're going to have to follow, alright? So pretty much, step 1 is going to be find M and N, and also find your pi groups. I'll just rewrite it. I'll say step 1, find M and N, and also your number of pi groups. Step 2, select repeating variables. So what do we know about the repeating variables? What do they represent? What do they represent? Nothing? Yeah. Close. Close. Whether no, so you choose some of the independent variables. You can't choose a dependent one. So no, can't choose dependent. That's correct. But what they actually represent are your dimensionless parameters. So they represent N, L, and T. Alright? So that's what you're going to pick based on. Step 3, do the math. Right. Do the math and figure out your powers. Alright? So I'll just show you what I mean. So part A, determine the number of pi numbers needed. You might get one more. Wait, hold on. Alright, so determine the pi numbers. Why does it keep fucking doing this? Alright, so. Bro, why does this keep going? Alright, so. How many variables do we have in total? How many parameters? 5. Good. Yep. 1, 2, 3, 4, and 5. Alright. So we have m being equal to 5. How about n? So n can either is the number of dimensionless parameters. How many do we choose? or they kind of give it to you, give it away to you in the next part. It's really good because we have a mass parameter, which is density, so this represents mass. We have time parameter, which represents the t dimension, and we have something for the, what's the other one? Length, which is just, this one or this one. Kinematic viscosity. Right, that represents x. Sorry? N, yeah, exactly. N is dimensionless parameters, set 3. So therefore, how many pi groups? Two pi groups, good. So you do m minus n. Okay, let's work out part B now. Choosing your repeating variables, density, time, and viscosity, complete dimension analysis. So this is 9 marks. This is going to be the bulk of your, why does it keep appearing? I'll just do it up here. Okay, cool. So we're going to choose density, time, was it? And viscosity. So density is going to represent an m parameter. This is going to be t, this is going to be l. Okay? What other parameters do we have left? Which other parameters do we have left? Surface tension and r. R is going to be the radius. Right? So we have remaining, we have r and surface tension. So what we're going to have to do, so to find pi 1, first of all, write out our repeating variables with an unknown power. So it's going to be rho to the power of a, t to the power of b, and viscosity to the power of c. Alright, and what we're going to do is we're going to select one of these remaining variables. So I'm going to select r. Then for pi 2, let's say x, t, y, z, and we're going to pick surface tension. I highly doubt you guys will get surface tension because the units or dimensions for surface tension I don't even know. I'll figure it out. But okay, so this one and this one. So I'll figure out pi 1 first. So pi 2 I'll put over here. Let's figure out pi 1. So what are the dimensions for density? Mass over volume, yeah. But what's volume in terms of dimensions? L to the cube, perfect. And or let's say L to the minus 3. Okay. How about T? Good. Viscosity. That's in units. L squared to the t minus 1. Okay. How about R? L, perfect. Because R is radius. Any questions on how I got that? Okay, good. So now I'm just gonna make like group them up into like terms. So m to the power of something, just a, times t to the power of b minus c, and L to the power of minus 3a plus 1. Yep. Yeah, plus 2c. Okay. So what do we know about the pi 1? What do we know about pi 1? What are the units for pi 1 or dimensions for pi 1? Yeah, exactly. So it's going to be L to the 0, T to the 0, M to the 0. So what I'm going to do now is I'm going to equate the powers for L, for T, and for M. So, yeah, A equals 0. How about for T? B equals to C. L. We know that A equals to 0. So we know that C equals to minus a half. Therefore, our B is also going to be minus a half. Okay? So we're just going to sub this back into the very first. What do we need pi 2? Because they told us to find the dimensionless pi numbers. And we know there are 2. Right? So therefore, pi 1 is going to be equal to density to the power of A, which is 0. So it's just going to be 1. I'm going to ignore it. T to the power of B, so T to the minus a half. Viscosity to the power of minus a half, and R. So we get R to the T. That's first dimensionless number. A lot of confused faces. Sorry? Yeah, so B minus C equals to 0, so B equals to C. Sorry, question? How do we got that? Okay, so pretty much pi 1. Pi 1 is a dimensionless number. True. So if it, that means it's got no dimensions. So it has to be L to the 0, T to the 0, N to the 0. Make sense? No worries. Yeah, R is just because it's a radius. Yeah, so it's a length parameter. Okay. I'm gonna bother to do pi 2. Shut up. Wait, what? I can't hear what you're saying. How do we know what to select? Well, in this case, they've actually told us, thankfully. If they didn't tell you, so you're going to have to pick something that represents M. So think about it. So if I didn't have any of this, right? Let's forget about it. So what I would do, firstly, is I would write the dimensions of each of them. So T is just T, M, L to the minus 3, L squared T to the minus 1. I don't know what the hell this is. And this is L, right? So obviously I can't pick R, right? So I'm going to pick between these. Which one best represents M, L, and T? So obviously T is going to represent T the best because it's time. Alright, so that's pretty much done. Now I've got to pick between L and M for these two. For kinematic viscosity, do we have an M term? Do we have an M dimension? Can we pick it for M then? No, we can't. Yeah? So therefore we're going to pick density for our M, to represent our M parameter. Make sense? And obviously this doesn't have, or this doesn't have, it does have an L, but it's to the minus power, so we don't really like it. Because this is a positive power, so we're going to prefer that over it. Make sense? Beautiful. Yeah, no, I'm not bothered to do this one. Part C. See, if the results of the experiment show that the radius for this, oh, I have to do part B for this. It varies as, I'll quickly show you guys how to do it. Let's talk about C. So we know that R varies for T to the 4. Right? What do we know about R? R is a function, not Reynolds number. R is a function of this, 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 and this. Right? We can also say that pi 1 is a function of pi 2. The reason we can say that, Buckingham's pi theorem. Right? It's the first thing that we learned in dimension analysis. So you can have that 0 equals to a function, no, you can't have that, sorry. We have this. Alright, so we're going to sub in pi 1, we're going to sub in pi 2. So pi 1 is going to be R over, I don't know what pi 2 is, so I'm going to figure it out in my head. What paper is this? What the fuck? I'm going to guess 2010. Fuck. Bear with me. 2016. By the way, the auto ones, I think I've already said it, they've got solutions. This one, here it is. So 2b, I'm going to figure out what pi 2 is in my head. Fuck. So yeah, it's going to obviously be... Oh shit. So yeah, I figured this out in my head. Right. So this is going to be a function of alright, so they've told us that this varies with t to the power of 4. Alright, so I'm going to rearrange for r. Alright, and converting this function into like a equation, I'm just going to replace it with a constant. I'm going to say constant times alright, hold on, I'll show you. I can't really explain it that well, but here it is. So this is our pi 1 on the left, that's a function of pi 2. Right? So we plug in pi 2, we're going to rearrange for r, so that's what I've done. Rearrange for r. Alright? And then, like, we're going to convert this into a constant times, because it's proportional to, right? It's a function of. Right? So we're just going to multiply by a constant. By the way, this constant that we're talking about, you can't really figure it out in this course. You're going to need to have experimental results to actually figure it out. Alright? So you don't need to worry about the constant that much. And this is proportional, or like, to 3 on 4. Or did I say to the power of 4? This should be 3 on 4. Hold on, let me fix it up. I don't think you guys will see a question like this, but I just want to go through it anyways. And yeah, what you're going to have to do is and then if this is equal to t to the 3 on 4, solve for n, because we have t on one side, t on the other side, right? And then you can actually find what your function is in terms of your pi numbers, right? And then you form another equation, essentially. Is this equation after equation? And here it is. N is a half. Yeah. And then you just constant, blah, blah, blah. You form another equation. Yeah, I don't think you get something this hard. This is like something you'd see in like an old ass paper, right? Yeah. Don't stress too much if you don't understand it. We've gone quite over time, 15 minutes. If you guys have any questions, you guys can come through fine. I did want to really go through, actually, also fill this out. Alright, give me a second before I go through that. I did want to also go through this physical modeling question. Oh, this is such a good question. Yeah, if you need to leave, you can leave. I'll go through this question. Okay? This is a really, really good question. So this combines hydrostatics, continuity, momentum, and energy.
Thank you.
Alright, no worries. You guys can leave if you want. If not, if you want to stay, if you want to do good, then like. Okay, cool. So this is a question from 2019 or 2021. A lot of people came up to me asking about this question. It's a bit hard, right? So they've given us a contraption. If you are leaving, just be quiet. Alright, so I can actually explain the question really quickly. Okay? So, where is it? They've given us a water tank, which has an inlet and outlet pipe, orifice, whatever. So this orifice at the bottom can be closed or open, right? Depending on what you want. So in the first part of the question, they've told us that it's closed, right? And what we need to find out for part A is what the mass of this block is going to be in order to balance it out, right? So we're going to use moments again at one point, right? So they've given us the diameter of the tank, which is this diameter. which is 60 centimeters. They've given us a water tank which stays constant, right? They've told us specifically that the water height stays constant, right? So it says over it's steady at 50 centimeters. They've also given us a discharge coefficient of 1. Okay, what that pretty much means is that the velocity just before it exits and the velocity after it, or the flow before it exits, just before, and the flow out after is going to be the same. Right? The way it changes is that flow after is going to be equal to discharge coefficient times flow before. Right? That's the relationship between the discharging jets and all that. Right? Okay, for your calculation, neglect the weight of the all that blah blah blah. Neglect energy loss, massive. Okay, we're not going to care about any pipe losses or whatever, bend losses, exit losses, entry losses, none of that. Okay. So looking at part A, I've drawn a diagram like this. So that's how you read through the question. Orifice is closed and it stays steady at 50 centimeters. So there's no flow entering or leaving the tank. Calculate the mass to counterweight the balance of the water tank. Right? So pretty much we're saying that this force, the weight force of the block, and the weight force used to that amount of fluid is going to be equal. Alright? Give me a sec. Alright. So a few key things. We can actually find the volume of that cylinder, of how much the water weighs, right? And to find the force, what is this? Hold on a sec. Okay, to find that force due to that block of water, essentially, we're gonna have to use this formula, which you guys might have seen in buoyancy, right? So force due to water is gonna be unit weight of the water times volume of the water, right? I should probably write out like this. Okay. So firstly, finding the volume, it's going to be rho g due to this times the volume of the cylinder itself. Right. So one way you can find the volume of the cylinder. That's coming. Right, is to find the area of this base shape, which is pi r squared or pi d squared on 4, and then just multiply by this height. Right. That's true for any prism, so rectangular prism, triangular prism. Find the area of the base shape, which is going to be either square or triangle, right? And you just multiply by the length of it, or the height. Did cover that in one of my workshops. Okay, so we found the force due to the water now, right? So this is going to be equal to 1386.86. Now, in order to counterweight the balance, right, the moments have to cancel out. Right, so we're going to have to take the sum of moments about the pinned joint, this joint over here. It's not really a joint, sorry. It's more of a triangle. Yeah? About this point, let's call it A. I don't know what it's called. So taking sum of moments, we know the lever arm from here to here is 3 meters, and from here to here is 1 meter. 1.2 meters. They've given this in the question as well. So if we draw like a force body diagram, essentially, it's going to look like this. Oh, horrible. Okay. Do some moments and you can find your m value, which you get to be make sense? Any questions about this so far?
Can you scroll
Scroll up?
Yeah.
Up to here?
Yeah.
Got you? Alright. If you want to take a photo, yeah. Sorry? Oh, this one? Yeah, it is. So, just as a block of water. Yeah. So, at the moment, we know it's... I should probably go through it. So, over here, it's going to cause an anti-clockwise rotation, so it's going to be positive. This one's going to cause a clockwise, so it's going to be negative. So positive, negative, and then you just solve for n. Okay. Okay, cool. Okay. I don't know what they're doing at the back. Okay, yeah, thank you. Okay, part 2. So, part B, sorry. If the orifice is fully open, but the water level in the tank stays steady at 50 centimeters, because of water being supplied through the inlet pipe, calculate the discharge Q, right? So, hold on. What we know is that some sort of inflow, some sort of outflow. We're trying to find the outflow, right? Oops. So what are we going to use? This is what I was talking about, by the way, the discharge coefficient. The flow going outwards is going to be the flow in the orifice. So the orifice is like just before, I guess, and then times it by your discharge coefficient. Right? So I've kind of put it in different terms here. This is what they have in the lectures. Right? So they would say actuals over here, so flow going out essentially, times the flow just before the orifice, times by your discharge coefficient. In this case, it's exactly the same. Yeah, so it's not that deep. Okay. Discharge coefficient. Yeah. They've given it to be 1. Okay? So now I'm going to use Bernoulli's between point 1 and point 2, where point 1 is the top of the water, point 2 is at the exit, right? It's at the orifice. So I'm going to say point 1 here. You can use Bernoulli's wherever you want, right? But you've got to use it strategically, right? If you use it at point 1 and point 2, right, you can only do you can find your answer in one iteration of using Bernoulli's. If you use it in like over here, and then you use it again for like over here and over here, right, you're going to be using it twice. It makes your working out much longer. So think about it. Make sense? So think about it. Be like, okay, we're trying to find the velocity or the flow at the exit. So I'm going to let one of my points be there. Where else do we know? What else do we know about? Sorry. What other velocity do we know? Right? We know the velocity at the top of the water is going to be 0. Why is it 0? It's not moving. Also, it's steady state. Right? So not steady state. The level of the water is steady. So anywhere at this point, the water is pretty much not moving. Right? So that's what I've done. So point 1 being up here, point 2 up here, right in the middle of the orifice. So what we're going to try to find is V2, or the outwards velocity, which we get to be 3.132. .5 times 2g. Okay, I'll give you guys a minute to put it down. Yep. Why is the pressure at 0? Over here. So pretty much the pressure at like the surface of the water is going to be 0. They haven't really told us anything about this one at the bottom. Yeah, so that's exposed to the atmosphere. Make sense? Yeah. So very similar reasons. So yeah, because the water is flowing outwards, right, into the atmosphere, the pressure, point 2 is going to be 0. Alright, and then after you find your velocity, you can find your flow, which is our answer here. Okay, the next part's a bit tricky, right? So part A, part 2 is like pretty chill, doable, right, with a bit of thought. Part C requires intense thoughts. It sounds kind of weird, sorry. Alright, part C. If the orifice is fully open, was anyone still copying down? Yeah? Okay, I'll go back. You guys, 5 more seconds. Okay, good. Okay, if the orifice is fully open and the water level in the tank is still kept steady, right? Calculate the mass. Calculate the mass. You guys might be thinking, because the water tank height stays steady, right? The amount of water is still the same, right? That's true. The amount of water is still the same, right? So should we get the same mass or not? How come? Perfect. There's a flow from the force, right? It's kind of to do with momentum, right? Well, to find it, you need momentum. But yeah, because of the water flowing outwards, there's going to be some sort of, like, you can think of it as reaction force going upwards, right? So in this case, we've actually got another force that we have to find. So we've got the force from the water itself, then we've got the force from the water flowing outwards, right? Then there's also the mass force that the weight force that we have to find. So anyways, here it is. Oh no, here it is. So I've got the force of the water and the force from the discharge of the water. So using momentum in the y direction, right? So in the y direction, so also there's going to be some sort of inflow here. So if I do sum of forces in the y out to in, this in part is going to be 0. Even though we have an inflow, y is going to be 0. Direction, exactly. So wait, I should probably write this as v. Right? So since we're looking at it in the y direction, right? The inflow in the y direction, there's actually no inflow in the y direction. The only inflow we have is in the x direction. How about outflow? We do have outflow in the y direction, right? But we don't have any outflow in the x direction. We don't care about x direction right now because we're trying to find the y, the force in the vertical direction. What the hell's going back there? So yeah, this part's going to be equal to 0. So going down, as no inwards force in the y direction, what do I do? Oh yeah, so sum of force in the y, that's going to be our F discharge, and then I'm pretty much just completing this over here. I forgot to multiply by density, that's right. Density, there it is. Alright, so Q outwards we pretty much found earlier. The V outwards we found even earlier, over here. So we just sub that in and we can find the discharge force. 12.3276 something newtons upwards. Okay? So whenever you're dealing with any outflow, inflow for a system, think about momentum. Right? That's something you guys should take into the exam. Right? Always think about momentum when you see outflow, inflow. Okay, then I'm just going to do sum of moments again. Blah blah blah. And you get your answer. Sum of moments I'm not going to explain. I'm pretty sure you guys all know how to do it. Okay? And yeah, that's the question done. For those still copying down, yeah? Original mass, it was 320 something. Never mind. 353. It's less because it makes sense, right? This is like some counteracting force. Alright, that brings us to the end. Yeah, question? F discharge times 3. So that's the force due to discharge times 3 because of the lever arm. Alright, so discharge. Yeah. Okay, for those who haven't done the registration form, please fill it out. Alright, right now, or else you're not going to be allowed to leave. So do it right now. No, this is different, for fluids. Because you attended your solid zone and fluid zone. So do it for fluids now. What? Yeah, you're meant to do the other one. Like, now, you can do it now. So we know you're here. Yeah, if you have any questions, by the way, come to the front. I'll pause the recording. I'll end the recording.